good afternoon, everyone. As Mark mentioned, I'm Keith. I'm with Datastax, and previously with Red Hat, so it's been a couple of years since I've been to one of these, but I'm kind of excited to be back and see everyone. I'm also coming off 3 days at reInvent, and if I never go there again, it'll be too soon. So like, I am super excited that it's like quiet and there's not 60,000 people. I don't have to like walk 4 miles to get somewhere. So here's what I've got. Hopefully this is kind of a good fit for folks. Datastax, we're a data company, and as with every data company, we wanted to kind of pivot and do some AI stuff. So all our marketing, all our branding is all AI all the time, right? But given this group, I wanted to kind of go a little bit deeper and talk about some of the technology and how our underlying database based on Apache Cassandra, how it works and why it works. And also spend a couple minutes talking about like some of the patterns that are being used with our data when you're doing some Gen AI stuff. So this whole terrible mouthful of a title, knowledge graph or graph rag, like this is one of the strategies that's being used more often to like surface relevant data that you might use to put in the prompt if you're doing some Gen AI with an LLM. So like that's what that whole word salad is up on top of there. Let me show you something first, then I'll get to some more slides. So this is my DevRel guys put this together. This is like 2 different kind of searches. This is not chatbot driven. This is just like form driven, but it's using vector search under the hood, which is, again, that's kind of what we power. And let me set this down and type. Or no, I'll even do this and type. You can hear me, right? Okay. So comparing 2 searches side by side. And when you're using vector search, the idea is you've got this intent and you're doing natural language search, and you're able to surface things based on intent, not based on keywords or something else. So I've got a database of all these movies here, and if I search for movies with a female lead, like that isn't any keywords, right? You're not going to come up with that. But with our tech running this side by side, you're going to come up with a couple of movies. So like Damsel, Idea You, Poor Things, right? So these are 2 different searches side by side. The one on the left is just like the naive way of doing things. I'll walk into details how that works in a couple minutes. The one on the right is like the new one, which is this knowledge graph, which we're seeing a lot more people do, that I kind of want to just introduce the idea. So similar results, they're both saying Damsel and Red Sparrow, right? So this is doing a search from our database, sending it to OpenAI and getting some results. So if you do a somewhat more complicated search, so movies with a female lead, not about love, then you're going to get a different set of results. And this is a little bit more complex to figure out the intent when someone's searching in it. So the naive requests to OpenAI, like that fails. There's no real results based on what we're able to surface. But using the new strategy, we're able to pull out some movies like Hidden Figures. The last little tunable here, and we'll talk about what this means, is when you're doing this kind of searching, there's this trade-off between having things that are similar to each other and then trying to introduce diversity to get different kinds of responses. So if we change that and then research it, you're going to get a slightly different set of results. So I guess we added Furioso in there. The other was already there. So that's kind of what this pattern is doing. But let me pivot away from that and kind of talk about how some of this stuff works, and at least academically, why you might care about some of this stuff. So here's my strategy, right? Spend a couple minutes kind of introducing Apache Cassandra as a data store, introducing my company, kind of why we're here, why we've got some credibility in general in the space. Spend a couple minutes talking about like vectors and vector search. Raise your hand, has everyone been through a vendor talk yapping about vectors and vector search? Legit, only like a quarter of you? Oh my gosh. Okay, So spend a couple minutes going through that just to kind of level set on some terminology, and then do this knowledge graph, like the new thing. So think of this as like your day at school. It's just kind of academic, but you'll kind of get conversant, and hopefully some of this stuff seems kind of cool. Like that's my goal. So introduction, kind of why are we here? So Datastax has been around since like 2010, I want to say. So is that 15 years? Collected a bunch of logos in that time. You know, some are consumer focused, web scale businesses, others are enterprises, some are highly regulated. Like the common thread across a lot of these is on the data side, they've got some common needs. Like they needed to be globally scalable, multi-regions with what's happening with their data. They needed really deterministic, low latency access to a lot of their data, durable data that can be highly available, right? So like that's the common thread inside of there. Where we are as a company, what we're built on, there's a project called Apache Cassandra. So this came out of Facebook in like 2010, 2011-ish, somewhere around there. So we've been maintaining that project through all these years. And then we also have kind of some commercial versions. So the same kind of play that Red Hat has. When Cassandra came out in open source, there were two big knocks against it. One was it sucked to be an operator, and two was it sucked to be like a data architect. It was just terrible, right? So we've solved for both of these. The first, if you're an operator, we did the same play as Red Hat, as every other vendor. We said, hey, let's do an enterprise version, make it easy to deploy and easy to secure and run it on Ansible or on Kubernetes or OpenShift, right? So we solved for that with software, Datastax Enterprise. We've also got a hosted cloud version, so there's just no operator role in there at all. We'll just kind of maintain it for you. So the first of the two things we solved. The second, I think, is more interesting. Again, since this might be more of an infrastructure audience, maybe not as interesting, we'll see. But the second was on this data model thing. So Cassandra was one of the first NoSQL databases. And in doing so, the whole way the data worked was like totally different than any other relational database. So even if you're not a DBA, I assume that you know databases have tables. A table usually refers to like an object of some sort, like a customer, a transaction, or a product. And then you'd have keys to define the relationships between these things. So you get all this stuff put in place, and then you can issue a query and get some beautiful results. Like that's the normal playbook with data. With NoSQL and with Cassandra, it's actually like the total inverse. Like you don't define this data model and write queries. Instead, you're like, okay, what queries are you gonna write? All right, what's the shape of your data? Okay, now I'll make a schema. Now I'll make a table that aligns to that. So it's kind of backwards, which makes it hard to use because you got to think about it so much more. We solve for that by putting some opinionated data models on top of that so that you can use this without thinking about Cassandra. You can use it like you kind of want to. So examples of that, we've got a Mongo compatible document model. So you can just like send a JSON record of any structure and we'll take it and you can query it and do anything magically you want. We've got like a schema-based graph. So think like Neo4j, that kind of a space. So you can traverse the graph and do sorts of things with vertices and edges. That's another kind of interface that we've got on top of it. And possibly, or yes, more relevant to what we're talking today, a vector type interface. So you can use that to kind of surface data using natural language. So that's kind of the magic that we put in there. So we got this vector search, and we're like, okay, like every other data company, we want to like be in the AI space somehow, right? Because that's the sexy thing. So this was our play. Our play was let's have the vector search, which by the way is really good. But then what else can we put in on top of that? So acquired a number of different companies and projects to kind of put together this non-opinionated stack of things that you can do for your silly chatbots, your silly Gen AI workload. So looking at this kind of top down, like if you're doing Gen AI, there's this user experience where you're interacting with something or writing a prompt and trying to get the kind of response that you want. As you go down the stack, there's this idea of how can we inject context-specific data? You go down even further into like that red cube. It might be how can we be more agentic or using tools, if that's something that you guys have run into in the past. Kind of all these different things, trying to make these motions a bit more powerful. And then at the bottom, it's all kind of anchored by data. And again, I feel like I know this crowd. I've talked with you before. So let's focus more on that tier that's a little bit closer to the infrastructure and how some of that stuff works. So on the data tier, Apache Cassandra, I've said that a number of times. We've also got kind of our enterprise edition and our cloud native version. They're all kind of the same from the architecture perspective, where this Cassandra design pattern, what was put together at Facebook, still kind of holds true. There were some of these like requirements when we were designing this. One was, hey, we want it to be distributed everywhere, not just within a data center, but globally across different regions. We want to make sure that the clients, that they can read and write anywhere, like no limitations there at all. And finally, want to make sure that the data that's stored is super durable. So having multiple copies of it so that if there is a failure of a node or failure of a storage device, it's kind of no big deal, right? That was how and why things were designed. So drilling into a couple of these in a little bit more detail. The data replication, usually see about 3 copies of each piece of data within a data center. So all that replication, you don't think about it as an operator, it just works. What's unique about it is there's not like a master or some kind of a witness or one of these other nodes that becomes a choke point or a failure point. Instead, all the nodes talk to each other, they self-organize, they self-replicate data across this ring so that as you scale, there's no additional complexity, right? There's none of these bottlenecks that you traditionally found with a lot of data inside of there. It is perfectly linearly scalable, and it can operate at web scale. A lot of my customers will have 1,000 or 1,500 nodes working together inside this database, so it truly is kind of like this consumer web scale, able to handle this. You can add additional nodes with 0 downtime. You can add a new data center, or if you're in the cloud, a new region, 0 downtime. So it's just kind of magic in how that stuff works. And as you scale out, like there's no change in latency. It's very deterministically low latency every query that you'd have. So that's kind of the selling point inside of there. Multi-region or multi-data centers, that's kind of how we can extend beyond a geographic region or kind of a latency zone inside of here. You can have as many of these logical groupings of data centers as you want. They can be as large as you want. What's kind of cool is the clients are actually kind of smart. So it's not just like a dumb client where you have a connection string and then you're done. Like the client itself has a little bit of control. So for example, the client, well, first of all, the client can read or write to any of those 1,000 or 1,500 nodes. Doesn't matter which one, right? But when the client is making that query, it can decide what kind of consistency level it requires of the data. So we are eventually consistent. That's how we solved this latency multi-region thing. The client can say, hey, it's super important that when I do a read, the data is entirely consistent. So I want to make sure that we have a quorum of consistent results globally across every region, right? That's going to be an expensive operation because you got latency between different regions. Or you could say, hey, kind of mid-level thing, I just want it consistent within this data center, right? I just want a quorum of consistent results there. Or if you just want to be fast, 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 you can say, I just want an answer from someone. I don't know if it's the result from right now or the result from a minute ago. I just want something right away. And we can get a result. So it's kind of cool about that, at least I think, is if you've got this database workload, okay, like you're doing like a batch load or doing all this analytics and you're just like hammering one of these Cassandra nodes from all that traffic. And at the same time, you've got some real-time ad hoc query that's coming down that wants to access that same data. There's 3 copies of the data. So the client comes in, it says, hey, give me my query to the 3 different nodes, and whichever one responds first, that's the result it goes with. So if you've got analytics or that batch weighing down node A, then you get a response from node B, node C, just as fast as if nothing else was going on. So from an operator perspective or an SRE perspective, it's like super consistent. So I don't know. I think it's exciting. Judging by your faces, I'm getting a so-so. So It is NoSQL, so it supports a subset of SQL. There's no like joins because it's just a single table that you'd work with at any given time, but the rest of the query looks kind of normal. Since I'm going to be talking about vectors today, this is how you might do something with the vector. You can sort by vector similarity. You can filter based on nearest neighbors when you're doing some of this natural language search stuff. That's Apache Cassandra. That's the software that we're built on. Before I get into my AI mumbo jumbo, questions? Yeah. Oh, that's on purpose. Yeah.
Before we go into AI, is it self-aware?
No. Although the stuff that runs on Kubernetes basically is, right? That's all operated up and uses crew and all these other things. That's self-aware with health checks and stuff, right?
So machine learning.
Yeah. There you go. All right. The disk doesn't matter so much at all. No, and even like the Astra DB, which is our cloud-hosted one, so that's rewritten to be a cloud-native database. It's using the same playbook as every cloud-native database. You've got tiered storage. You're using like object storage at for the bulk of your data, and then you have things cached, indexed that might be on the machines. So it's like that same playbook. And like object storage latency is just terrible, time to first byte, right? And you still get these, single-digit, low single-digit millisecond response times. So disk largely doesn't matter. When it's deployed in the data center, disk still doesn't matter that much. We like to see like cache and memory, and if people are hitting some of the same things again, to be able to take advantage of indexes and some of the more recently used things. So you can kind of tune configuration for that a little bit, but that's largely self-correcting. What most people do is, it's not about a better, faster disk, better, faster I/O. It ends up being more nodes is how you end up kind of scaling out, whether it's just more stuff that you have or it's more traffic. Ends up being the standard play. Yeah?
You mentioned clients of 1,000 nodes, 1,500 nodes. Are those like petabyte databases? Are those?
Yes.
Why you would go that size?
100%. It's either the total volume of data that you have or the amount of concurrency that you end up doing. So it ends up being either of them can end up driving it. Yeah. So a 3-node cluster running in the cloud, I mean, I'll see 80,000 transactions per second is what it would support. So certainly if you're running the data center, you'll probably get better performance because it's real hardware. But you can definitely do a lot with this stuff. All right, so we move up the stack a little bit, going to vectors. So like here's how I think about vectors, like in the context of searching. Start on the left, like simplest search that we can all picture. It's a keyword search. It's like an echo join. You get a subset of things where this matches. And that works super well for structured data, anything you'd have in a relational database. That's keyword search. So moving right along this continuum, excuse me, you can do a full text search. So this is Elastic or anything with leucine, where you've got like a needle that you want to find in a haystack of some sort, or maybe a phrase that you want to find. So this is going to get you a larger set of results, starts working a lot better with unstructured data. You can do things to tune full text search, right? You can do, the words don't need to be together, or you can do some distance functions to account for misspellings, or you can build synonym lists to do a better job of catching things inside your search. But it still requires either a ton of maintenance or forethought of the folks who are operating and building the data model, or it's still not going to be able to capture search intent. And so when you think of natural language search, that's what we're doing. We're capturing search intent. So if there's synonyms or other kind of descriptive words in there, or that silly example I had before of movies with a female lead for my movie database. I mean, it's pulling that from all like the synopses of the movies from IMDb. It's trying to get my intent. Vector search and vectors and where we play, it's in that natural language space. And we're able to deliver natural language search results by vector search. So what's a vector? Someone in the back asked. So a vector is a point in a multi-dimensional space. So if this is the first time you're hearing this, probably makes your brain go a little crazy. So think back to math class, image on the right, that's like 3 dimensions, right? You've got an x-axis, y-axis, z-axis. And every one of these little things, that's like a point in that three-dimensional space. When we're doing vectors and we're creating vectors, we want to see things that are similar to each other being near to each other on that graph. So in this contrived example, we've got animals that are kind of on the same plane. On the right, we've got like fruit and banana similar to each other, but you know, Apple, the fruit, Apple, the company, they're also kind of similar, right? That's kind of what happens when you have these different vector points. So in order to power natural language search, we need to find a way to convert the text that you're typing or an audio file or an image. You need to be able to point that to a specific place inside this vector space that we have. And the way that we do that is we have this machine learning trained model that's trained on data similar to what you're working on. You can pass in some data, you know, usually text, but it could be audio or a picture. You pass that into there, and the model has these weights that says, oh, well, you know, apple is kind of like this, and a chicken is kind of like that, and the output ends up being just this mathematical representation of how that data fits in the model. A lot of kind of gibberish there. It's mostly just magic unless you're defining those models. But this is the first step for powering natural language search is let's find a way to mathematically represent that phrase of things that you might be typing in. Step two is to actually search for it. So if you're searching for things, it's really hard because it's not like a three-dimensional space like that cube. It's 1,500 dimensions, right? There's just tons of complexity in there. So then we get to like math and algorithms and kind of figuring out how to do some of this other stuff. This is currently the best way to search for vectors. It's called hierarchical navigable small world. And it's where you say, okay, here's our 1 trillion objects, and we kind of go through each element of that vector and slowly reduce the radius of things that are similar as you go from layer to layer to layer. This is what all of the fastest vector search engines currently implement. It's still kind of trash. Like, it's better than things were, but like two big drawbacks are if you are deleting data, you like end up having tombstone records usually inside of there, so that's going to slow things down. Or if you have a ton of data, you have to have all of this sitting in memory in kind of one node. Like, there's not a great way to partition this like we've done with everything else as we get kind of cloud native. So there's like scalability issues inside of there. So my company, we sponsor a project called JVector. It is the fastest Java implementation of vector engine. It's implemented like this, and they've done tons of tweaks so that you can fit a lot of objects in one piece of memory. So we've done the best there is, but I'd expect there to be like advancements in time. Okay, so you've got your vector search. Someone entered in a query, you know, movies with a female lead like I have. So that's our user input. And then we hit our database that tries to find records that are similar to that language. They're near to each other in that vector space. And then we pass that into like the prompt for our LLM. And then we throw it to the LLM, which does some magic and spits out a bunch of words. And hopefully they're the right kind of words. Like that's the pattern. So the name of this pattern is usually called RAG, Retrieval Augmented Generation. It's how you make sure that your Gen AI stuff isn't just working on old data, but it's things that are contextually relevant to like a customer or a business process or wherever you'd be implementing something like that. So that's the naive way to implement things, but it's gotten a lot better. What I found working with a lot of people is they like implement a chatbot for something. Like they ingest a bunch of unstructured documents, like internal documents. It's like an internal chatbot. They hook it up to Slack or something else like that to serve as like a knowledge base or to kind of help communication. Like that's what everyone does first in this space. And it works really well in the lab. And then as soon as you put it out in the wild, it just is just trash hallucinations and gibberish that's coming out. So we're able to solve for that with this knowledge graph. So building up to kind of the last thing here. In knowledge graph, we're able to incorporate more than just like a couple of words or a chunk of data. We're able to understand how things are connected to each other and build that connective tissue. So take this example. This is an example search. Let's say you're in a chatbot and you say, my phone's not making noise when it rings. It's on silent mode. So for this chatbot, you could have populated it with this knowledge base article on the right from Samsung. And the way you'd normally do this is it's unstructured data. You just kind of slurp it up. And you usually like chunk it by like paragraph or something like that. So we've got a few different chunks of data inside of here. And then when someone types into the chatbot, they say, hey, how do I fix the volume on my phone? We search for the closest thing, which ends up being that black box, I think it says, that says, hey, your phone's not making noise because it's on Do Not Disturb. That gets passed to your OpenAI LLM or whatever you're doing. And then this junk in yellow on the left, that's what gets spit out, right? And with this naive approach, that step one is wrong. It's just like making something up, okay? Because it didn't have the full context. So worked in the lab, but it fails when we're actually trying to do something. So if we're doing this knowledge graph, what we're able to do is same question, same set of data, but you retrieve that black box first, and then you realize that it's right next to this other chunk. There's a relationship established between them. You're able to pull both of those chunks together, send them to your LLM, and then in yellow, what gets sent back in the chatbot, now it actually aligns perfectly to the actual data that you had found in this stuff. So kind of a no more hallucination thing. The data is grounded. So that's what we hope to deliver. When you're parsing unstructured documents and trying to like seed the data for something like this, like a question and answer bot, what you can do is look at this document and just like us with our eyes, we can kind of see how things are related. Like they're all on the same page, they're kind of laid out in a special way. But when you have a machine parsing this, it's just going to do it kind of top down chronologically is what you're probably going to see. A slightly more complicated document is kind of a better example of what we like to do with something called knowledge graph, is we see the relationship. So each one of those paragraphs would be a chunk that you'd run through this vector engine and be able to search, but you've got like subheadings in pink, and you've got this heading in blue, and you've got images, and you can establish the relationships between all of those things so that when you query against it, after ingest, when you query against it, you're able to pull in a lot more context and give a better, more grounded answer. So there's two ways that you can get some of this data in. There's this idea of this fine-grained approach where you take all the data and you try and really figure out what it's talking about. Are there keywords in there? What are the relationships between things? I know I tried some of this with some of our products, and you like take a chunk of text and you throw that through an LLM and it extracts out keywords and tells you some stuff. And you have these really precise relationships, right? It's almost like it's structured data. It's really kind of nice, right? Or you could have something that's coarse-grained, where it's based on almost the document layout and how things are linked together, right? So what we find is these two have like the same performance, and this fine-grained stuff is really expensive to produce. So I ran a test against Wikipedia, and then I extrapolated out about a bit. And if you're doing this fine-grained approach, let's on ingest make everything perfect, it'll take like 6,000 or 7,000 hours to run through their entire corpus. Or if you can do the quick and dirty coarse way, it'll take like a couple hours. So huge difference in terms of cost, and you get the same results. So that's what our tooling and our algorithms generally end up doing, is the quick and dirty way with the same result. So here's how the search actually ends up kind of traversing to add in that additional context. If you do that vector search and you land in number one, you're able to find out one chunk of data, one interesting piece of data, and then you're able to find its relationships by following those edges on the graph. So some of them are stronger relationships, some of them are kind of weaker signals, but you're able to bring these in. And then there's this way where you can kind of balance between having a lot of items that are very, very similar and then items that are very different, and try and get a certain amount of diversity inside of there. So that's what I kind of highlighted in this first area. There's this diversity slider. So we're saying how many different items do we want to pull as we kind of pull that thread and get these things that are slightly related to each other. So it's kind of like this iterative process to get the right kind of result, to get things to run. So feel like I'm losing some of your attention here, so let me very quickly just wrap some of this stuff up. Things are linked together, and there's ways that you can go beyond this to kind of figure out, again, how can you identify someone's searching intent and match these things up in the best possible way. There's ways you can do some pre-processing so you get better results. And here's how you would actually implement this. So it's super easy to implement from like the old style to the new style. You like change one line of code, you just import a different class, and you're able to start getting access to some of this stuff. And when you're doing the queries for data that's going to power the chatbot or whatever it might be, here's an example of what the queries look like. It's super easy, which is why every single company at reInvent early this week had AI all over their booths, because it's like really easy to do. It's hard to do it well, but it's easy to do and get something. So here's 3 examples. The top one, this is how you get things that are most similar. Just doing the naive search is going to give you the 4 closest results to whatever your search query was. The one in the middle is going to start using this knowledge graph, where it's going to get the 4 most similar results, but that's going to go out 2 additional degrees and get things that are related. And all of this is going to be in the context for a prompt that you're going to throw at your ChatGPT or your LLM or whatever it might be. And the last one is the most complex way you can do this. Still looks pretty simple though, right? The most complex way. And that's where we're saying, hey, we're going to go out to 2 different degrees and pull in these additional linked data. But we're going to do this trade-off between duplicate results and having only some that are similar and try and favor things that are diverse so that we get a more well-rounded view of kind of the whole universe of what we're searching for. And we pop that context in the LLM, and the words that spit out of the LLM are hopefully exactly what we want them to be. So that's what I had. I wanted this to be a little bit more academic, just to kind of think about how some of these things work, why in some ways it's super easy and why you're seeing so many people doing it right now. But in order to go from like 60% accurate to like 85% accurate is really hard, and a lot of people aren't doing it, and why there's so few of these kind of like chatbots or other interfaces that are actually in production across all of your enterprise data. So I'll pause. Any other questions on some of that stuff that I can dive into? In the back.
Yeah, what impact do cookies or web browser history have on the relation, like how we use the data?
That's one of many signals that you can have to try and get the right kind of context inside of there. So when you're feeding data into any of this stuff, there's 2 kinds of data. There's your structured data and your unstructured data. If it's structured data, this is something that's in a relational database. Like you've got a cookie from your login session. We know your account. We know everything about you already, and we can like cherry pick that information and perfectly include that in the context for your prompt. So that's the easy problem to solve. The hard one is where it's mushy, like, okay, let's ingest everything from like a knowledge base so we can give the right kind of address, or the right kind of feedback to your question. And there, like your personal context, it's a lot less helpful, unfortunately. So, all right, I will turn the mic on over and get back into a different kind of weeds.
Yeah.